Hi, welcome back everyone. So this is the second part of the paper 1 2024 video. I'm just going to start with the question number 11. I hope you had your 20 minutes break. Now again, the idea is same. You pause, solve, and then play to see how I am solving it and to understand what was the gap in your thinking process. So I'm going to pause. So not me. You're going to pause it and do question number 11. So welcome back. I hope you've paused and solved this question. It's asking about the moment. So you can either write the equation of the moment, which is force times. Now this is important. Some of the students just write perpendicular distance. That won't get you the full mark. You have to explain the perpendicular distance is between what. So distance is always between two things. So this one is the force between line of action of force, that is important. So the line along which the force is acting, line of action rotation or axis of rotation. So in this case, this is the point of rotation, this is the weight, so this is the moment perpendicular distance between the line of action of force and the point of rotation. Now the question number 2, this one, if you have already tried it, you would know that this is a little bit calculation heavy questions. So now sometimes, as I was marking in the papers in the past, this is a common mistake that the student do, that they do try to do all of the calculations in the calculator. So in that case, what happens is there are some errors sometimes. So what we're going to start is make the equation first. Let's see. So there's this weight of the gold acting on the, so I'm just going to see what's the weight of the gold. The weight of the gold is 31,000 newtons and the weight of the bank robber is 8,700 newtons. So this is 31,000 newtons. I have the printed paper here. I'm just going to use that. Okay, so this is 31,000 newtons. This one is 8,700 newtons. Now the total length is 11 meters. So this from the center of the bus would be, its entire distance is 5.5. Take away 1. So the distance of 8,700 is 4.5 meters. This is 1.5. So the distance of 31,000 plus y, because we need the distance from the pivot, not from the center. And the distance of 31,000 from the pivot would be, this distance would be 4 meters. So this one would be 4 minus y. Okay, if you have not understood, just pause it and see what I've done. I've just marked the distances. Now, now let's just see what is it asking. I'm just going to read it from the question paper, so I don't want to change the screen. Calculate the distance y when the bus is balanced. Now, if the bus is balanced, the total force is, of course, now we have missed out on one thing. We have missed out on the weight of the bus, which is 32,000 newtons. So the weight of the bus is going to act at this point, which is 32,000 newtons. And the resistance from the pivot is 40, is y. Now, as you can see, this force would produce a clockwise, these two will produce a clockwise moment, and this one would produce anti-clockwise. So when it is balanced, clockwise moment is equal to the anti-clockwise moment. So I'm going to just take some space in the next space. So I'm going to just do it here. So make the equation 32,000 times y plus 8,700 times 4.5 plus y should be balanced by 31,000 times 4 minus y. That's my eraser. So that 4 minus 1. Solve it using your calculators or whatever. So the answer that I got was y equals to 1.18 meters, which of course can be done as 1.2 meters. So that's it. Okay, now so start with the distance 5.5 meters, 4.5 meters. This is 4 was the distance of the weight of the bus from the pivot, weight of the persons from the pivot, and the weight of the gold bar from the pivot. So that's about it. So if it is anything other than 1.2, the bus will fall into the ditch and they cannot steal it. All right, let's see the next one. You're going to pause it, and then you're going to start. All right, welcome. If you've done it, let's just see. So now this is asking whether the claim for efficiency is correct or not. So now the power transmitted from the Norway is 1400 and the transmission potential is 1100 kilowatts. So you would know that when the power transmits from, so they're giving like 1400 here from Norway, which is 1400 million watts. So what's the power that is being received at the other end? So the power that is being received at the other end would be 1400 minus the thermal losses. Now you can calculate the thermal losses is nothing but the losses that's happening because of the heat produced, that is I square R. So now what I need is the formula for the resistance, which is rho L over A. Calculate the resistance. So I'm going to just plug in the values. Rho is 1.7 10 to the minus 8. Length is 720. Be careful of the units. Times 1000 kilometers. Area is, so because it has diameter of 15 centimeter, this is 15 centimeters, area would be pi r squared. R would be 7.5 10 to the minus 2, converting centimeters to meters. So this, if you just plug in all the values and resistance, I did it earlier, this is what I was getting. Let's just have it. My resistance is 0.693 ohms. 3 ohms, I got my resistance. And then you need to also, I think, you calculate I. So what's the current? So I have, the voltage is given, the transmitting potential is 1100 kilowatts. So I would be V over R. 1100 is times 1000. And resistance is 0.693. So once you've calculated I and R, you can calculate the output power, the power that is being received at the other end, which is, so this one is just coming as 1.12 million watts. Okay, you need to convert this into million. Now, as you can see, the loss is very less. Almost as compared to 1400, the loss is only just 1 million watt. So either what you can just do right here, that the loss is less as compared to the input power, or you can calculate efficiency. So the efficiency is output, which is this, and divided by the input times 100. So when you calculate this, what I was getting was around 99.9%, which is almost 100% efficient. That's it, quite easily done. What they're checking is when you transmit power through a long distance line, this is the losses that occur. So they just need to see whether you can calculate that. And they have just, because it's a simple concept, they have increased the complication in terms of the units. Here, centimeters, then here, I think you had it in kilometers. So be careful of the units conversion, be careful of the calculations. These are short marks because they are not the complicated ones, they are simple questions. Okay, let's do the next question, number 13 then. Now question number 13 is, again, I want you to pause the video and try it yourself. If you have done it, then welcome back. Let's just do this one. Show that the rest mass of an antiproton is about 900 million electron volts over c squared. So what you do is, you need to show that the mass of antiproton, you need to know this, that this is what they're looking for, that's your first mark, is equal to, the mass of proton, the rest mass of proton. Okay, so first we do this, which is 1.67, that comes, by the way, come from your equation sheet, we're done, and then you convert rest mass equals to mc squared. So 1.67 10 to the minus 27 times speed of light 3.10 squared. Now this mass is in kg. Now, but they want it in million electron. So sorry, this is rest mass energy. So this one is in joules. Now, to convert this into electron volts, you need to divide this by 1.6 10 to the power minus 19. That is the charge of electron. Done. Then to convert it into millions, you need to divide it by 10 to 1 million. Okay, so that is 10 to the power 6. That's done. Then this would give you around 900 times 3 into 10 to the power 8 c squared. I'll just give you the example. I was getting 939, so let's just put that value. Okay, so this is 939 and divided by 3 times 10 to the power 8 squared, so that this is 939 million electron volt over c squared. This is your c squared. So it's kind of a weird question. They're asking you mass in terms of the units of energy and speed of light. So see what I've done. Pause it and just see what I've done. If you have not done this, just check your calculations and just redo it. That's it. Okay, let's do this one. Again, pause. If done, let's start. Deduce by using conservation law whether it is possible or not. So what conservation laws? Let's start with the first one. Conservation of charge. Is it conserved? Let's check that. Do you think that the charge is conserved or not? Positive, 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 negative. Yeah, so done and done. So yes, the charge is conserved. Say from the point of view of the conservation of charge, this is possible. So that's your 1 mark. Then you do, is the conservation of baryon number, conservation of baryon number, let's just say what's baryon number. So let's just see what's the baryon number. So the proton has a baryon number of 1, so 1 plus 1, 1 plus 1 plus 1 minus 1 antiproton. So yes, it is definitely conserved, so that's your 2nd mark. Now the most important 2 marks. Why? How is this possible? So we just calculate this one is kind of a scaffolding for you for the next question. How much is the rest mass energy of an antiproton? 900. Okay, and what's the rest mass energy of the proton and the proton? It's the same. So what's happening? If you see the conservation of energy, so you have 900 here, you have 900 here, this is 900, this is 900, this is 900, this is 900. So in what case can you conserve energy for this equation to be possible? That means you should have this extra 1800. How would you get this 1800 extra from these 2 colliding protons? So for that to happen, for conservation of energy, the beam of electrons, the colliding protons, should have an extra kinetic energy, should have extra kinetic energy of 1800 million electron volt over c squared for the energy to be conserved. Actually, little higher than that, because initially there was no momentum. So yeah, finally they can be at rest. So to be get it. So this is the only trick here. Tell you, use what you've got from the previous question into this question by understanding that antiproton should have an extra energy of 900, and there's an extra proton should have another energy of 900, even if it is at rest. So the colliding protons should have an extra 1800 million electron volt per c square energy for this reaction to happen. That's it. Okay. Pause for the question number 14th, and if you're done, then welcome. Let's start. So you have a decay of a positive muon produce a positron and an electron neutrino and antineutrino. The diagram shows the track formed by the particle detector. So take 2 features that all the particles in the lepton family have in common. So what's the important part for the lepton family to have in common? 2. First, each of them should have an antiparticle. That's the most important thing. Any lepton family, each of them should have an antiparticle. Okay, that's it. Because it's a 1 mark, no, 2 marks, so you need 2 second point. So the second point for gas word. Shout out. Good. So if it has a lepton family number, the baryon number should be 0. Okay. Or if it's a 3rd mark, we can also write the lepton number should not be 0. That's it. Okay, let's do that. Write a nuclear equation for the decay of the muon described above. Let's just go above and just see. So decay of the muon, what is happening? So you have a muon decaying into a positron plus an electron neutrino plus muon antineutrino. That's about it. Now the 2 marks, if you do not put this, or this, you don't get the marks. So make sure you write everything about that. Describe the role of magnetic field in a particle detector. Now this topic has gone from particle physics to magnetic field. So we're just going to talk about the magnetic field now. Why do you need a magnetic field? What is it doing? So see, I'm pretty sure you know that, but I'm just going to still talk about it. So this is a different circle. This is a different circle. Who's giving them the circular path? The magnetic field. Okay, so the magnetic field provides the magnetic force for the circular path. Okay, and then because circular path, second, as particle changes, the radius would change. Okay, so if it is a different radius, we know that the particle is different. So that's the first point. So if there is no magnetic field, we wouldn't know that the radius has changed, or there's some change, there's a new particle being produced. And the direction of the radius, direction of the curve would tell us whether the particle is positive or negative. Okay, direction of curve, what would it tell us? Particle is positive or negative. Done. 4th point. So this is the understanding. You start getting marks from this point. Okay, so let's not just do this once. So this is the 1st point, this is the 2nd point, and now the 3rd point. What else does the magnetic field does? The radius helps to calculate the momentum, which helps to calculate momentum because it depends on the charge and the particle. That's it. Done. That's the role of the magnetic field. Okay, next to that one. Explain how the diagram gives evidence that a particle or particles other than positron were produced in this decay. Let's start first. Radius is different, right? You can see that. Radius is different. So different particles. And because particles are different, to conserve the momentum, oops, sorry about that handwriting there. Okay, so to conserve the momentum, another particle has to be there. Another particle has to be there. I think that's about it. So it's okay, so that's it. Let's try another one. So the video has gone for 19, so we are starting for 20 minutes. Let's start this question. When you come back, well, let's just take a pause, take a minute, and we can start another video for question number 15. Thank you.